All right. Sections 1 and 2 in the book have some 1 and 2 of chapter 5 have some basic concepts about like properties of water, um, how much salt there is in the ocean, what other solutes exist in seawater. And you get some time to like look through sections 1 and 2. In the study guide, in like the section 2 thing, water is very peculiar in that it exists as a solid, a liquid, and a gas on Earth. It can be at the same temperature at the same location. So I don't know. Let's talk about this. What are the different ways that the different states of water? This is like at the top of the second page. Exist and like where they exist, not just in the ocean, but like in the atmosphere in total. Let's go back. Previous next page. So like water can exist as a solid, as a liquid, and as a gas. I don't know why this thing's on here. That's kind of weird. So I can drag this to a different screen. There we go. So how does water exist as a solid? Ice. You know, let's talk about ice for a second. You know, like you can have ice in the ocean, and there's two kind of ice that happen in the ocean. Do you know what they are and how they end up forming? Like, give me one example of how, like, where you'd see ice in the ocean. Yeah, icebergs. Do you know where icebergs come from? They do. They break off of glaciers. So if you have, can have icebergs, and so if they come from land, are they freshwater or are they saltwater? They're fresh. Yes. So icebergs, they are fresh. In other words, it's like ice and snow falls on land, and then the iceberg, uh, we say it can't. Oh, we got a fire. Yeah, this is not a drill. So out to the loop.
Please pardon the interruption. Please stay in your room. Please stay in your room. This is just a false fire alarm. Taking it for free. I'd rather go inside than listen. Hold it.
I don't know. Okay, so I don't know. I'll draw like here's like land where it meets the ocean, and you can have like an iceberg. So, or you can have like a glacier. So you have a glacier, and as the glacier moves down into the ocean, it'll calve off, and you get these icebergs. And you might know that like a lot of the iceberg is underwater, and some is above the water. So the ice for an iceberg is actually fresh water. And there are places on the earth that have like shortages of water, and there have been proposals and ideas to like, hey, you got some kind of desert region that needs some water. Grab one of these icebergs and tow it down there. You know, it's a bunch of fresh water. The Titanic hit an iceberg that was from a calved glacier. So there's icebergs. So that's a thing. Was it you? What's up? I got this. All right. Thanks. Bye. There's Mr. Harris, because he like burned the school down like 4 times in 2 years this one time. So we have this joke that like it's Mr. Harris burning the school down. So he was calling around to let people know it wasn't him. That's why when I answered, I'm like, was it you? He didn't really burn the school down. So there were like, I don't know, in one year, there were 2 actual fires in his room that set the alarm off. See, like, I don't know, where is it? It's not that thing. Oh yeah, see, they're up here. There's like those there's like smoke detectors. So we used to have heat detectors in our science lab. They just detected like heat and not smoke. There's actually like lots of experiments we can't do now because you used to be able to have like, kind of like a mini explosion, get a little bit of smoke, and it was totally okay as long as it's like contained. Um, Also, like smoke machines will set them off. So it was really disappointing because when they renovated the school, they got rid of our heat detectors and put in smoke detectors. So now lots of experiments we used to make smoke with can't do anymore. Otherwise, we got to evacuate the building. So one of the times it was like an accidental fire, and the other time it was like a demonstration that was done for years and years and years, and all of a sudden set the smoke alarm off. And then we have to go outside, we have to wait for the fire department to come. Fire department has to investigate. Then they let us back in. So it's kind of annoying. Anyway, so icebergs can form where it's glaciers that fall off onto ice. But especially at the North Pole, you can also have ice that forms in the ocean. And that's called sea ice. And sea ice, or it's also called pack ice, is ice that's actually like if the ocean gets really cold, and it takes a lower temperature to freeze salt water than it does fresh water, but that sea ice will also form, and the sea ice is salt. So it's salt water, kind of like an ice. So if you are out in the ocean and you pick up a chunk of ice and you're like, I wonder if this came from a glacier or if it formed in the ocean, taste it. It tastes salty. It's sea ice, pack ice. If it's fresh, if it's just fresh, it's just ice. So where these glaciers end up forming from is just from snow. So, snow is a form of solid ice, but we're not too interested in snow because although it can snow over the ocean, as soon as the snow hits the ocean, it just melts. So that's not too exciting. But the formation of ice can either be from icebergs or from glaciers. Yep.
If you space an iceberg, wouldn't it still have like a layer of
On the outside, yeah, but not much because what happens, I mean, as it melts away, it's the outside layer that's going to melt away. But yeah, it depends on the glacier. Some glaciers, it's really, really dense. Here, let me get. It depends upon the way in which the ice forms. Let me get to new share. Okay, so for instance, here's a glacier that's, melting off a land. It's like a river of snow, enters the bay and falls in. Sometimes that snow at the top of the glacier is, not really densely packed, but at the base of the glacier, the snow can be so densely packed that it's pretty much like almost clear ice, like solid chunky ice. And it's not the snowy stuff at the top that would be valuable, but it's the yeah, the hard dense ice at the base that wouldn't be so, snowy. Does that make sense? I don't know why they're let's see, ice from type frog glacier. Yeah, like this, like blue ice. So it's like a densely packed ice that's at the base of the glacier. And a lot of times when the iceberg does form, the like the greater density stuff is actually down at the bottom, and the lower density snowy stuff is like at the top. So all the stuff that's underneath is pretty much, freshwater ice. So whenever you look at, let's do um, North Pole ice extent. This one's all right. So if you look at the North Pole or look at the North Pole from space or from a satellite, you can see the extent of that sea ice. So this is here's like North America, this is Canada, this is Greenland, and then Russia is up here. And this shows like an extent of sea ice. So this is not ice that formed from glaciers. This is because you're at the North Pole, and this is in September, so this is actually late in the summer. This is sea ice or pack ice that is all salty kind of ice that is formed right in the ocean. And I can show you how that moves because it moves by ocean current, and that's going to be a very important idea. Let me get to YouTube. All right, North Pole Sea. I have some really like good videos that I've already found. This one's okay. There are currents that move around at the North Pole anyway, in the North Sea. And as those currents move around in a circle, it carries the sea ice around, and that sea ice can leave the polar regions and end up coming down into the Atlantic Ocean, especially, but sometimes into the Pacific Ocean, usually just the Atlantic Ocean, because the Bering Strait is really narrow and the current goes up into the strait, so can't really get out. I think we're waiting for here we go. So I know that this is a little bit choppy, but up here it shows by day, and this was from in 2016. So we're getting like into the winter, but then as this runs into the spring, then you get more sunlight and warmer temperatures at the polar region. Here you can see the motion of the sea ice kind of coming down into the Atlantic Ocean. This is Greenland, this is northern Alaska, and then Russia's up here. This one's even better. It's yeah, it's actually pretty choppy on there. Yeah, that's not so bad. You can see the sea ice kind of moving around and swirling around and whatnot. The greatest amount of ice formation happens right here at the pole, but because the current is kind of in the clockwise direction, and some of the pack ice can then comes down along where Greenland is and head down into the Atlantic Ocean. The same thing down through here. So that sea ice is very, very common at the pole. The North Pole itself is not land, it's water. And sometimes it's open water. It's just straight up. You can be at the North Pole in a boat in open water. It could also be, pack ice. But the thing is that ice is constantly drifting around. So you can't go and stand on the piece of ice and be like, okay, I'm at the North Pole and expect that to be the North Pole even an hour later. Because as the sea ice moves around and drifts around, the ice ends up getting carried all over the place. So anyway, yeah, those are the two major forms of ice that happens in, or solid water that happens in the ocean is both icebergs and sea ice or pack ice. All right, then liquid water, well, that's easy, just water. But the thing about liquid water is we find it in all different kinds of places. And we're going to do a water cycle lab that's particularly focused on the ocean. So liquid water, I mean, we definitely find it, in the ocean. And then you also find it, in lakes and rivers. And lakes and rivers play an important role in the ocean because uh, like the Susquehanna River, which flows through Williamsport, it goes down to the Chesapeake Bay and it goes out into the Atlantic Ocean. So every bit of water on land, it ends up into the ocean, no matter how it happens. You can also have rain. And the thing about rain and moisture in the ocean is most of the rain that happens on land comes from the ocean itself. So like whenever we get, rainstorms, sometimes it's from the Atlantic Ocean off the East Coast, but most of the rain we get here is from the Gulf of Mexico. It gets uh, carried up from the Gulf. Sometimes it rains here because of evaporation off of land, especially like late in the summer when you get those afternoon thunderstorms and whatnot. But then water also exists as a gas. So we have water vapor in the atmosphere, and the water vapor that ends up in the atmosphere comes about from a couple different ways. It comes about from evaporation and another process called vaporization. And those two processes are different. Evaporation is whenever water changes from the liquid phase to the gas phase at temperatures below the boiling point. This happens below the boiling point. But then vaporization happens at the boiling point. So how do you end up with water evaporating on the Earth at the boiling point? Well, we have hot springs, geysers. You can have volcanic vents that can cause water to be vaporized and change into a gas. And that water vapor then goes up into the atmosphere. Whenever you see clouds, it's actually droplets of water. But as the water moves around on the planet, it's moving from primarily the ocean. Most of the water is in the ocean. It gets carried up into the atmosphere, gets moved across land, rains down as rain, can form ice and snow. And the ocean is involved with absolutely all of it. The origin of the water is oftentimes from the ocean, and all the water mostly ends up back at the ocean at some point. There's water that can be trapped, in the ground as groundwater, but a lot of times we pump it to the surface, we drink it, we, you know, use it for irrigation, and all ends up back in the ocean. So water acts as a big solvent to carry stuff around. So naturally, water can exist as a solid, as a liquid, or as a gas, as ice or snow, in glaciers, in snowpack, sea ice or icebergs. So from now on, when I say sea ice is ice that forms in the ocean because the ocean gets very cold and it's salty. Icebergs are commonly, the process of the iceberg breaking off the glacier is called calving, which is kind of a weird term, but it's like as a cow gives birth to a baby, that baby is a calf. So just the same as you have this big iceberg, it gives off little baby pieces of ice. That process is called calving, like Calving, like to have a calf. That doesn't mean that we call glaciers cows, but the process is calving. All right, so those are common ways that we find water on Earth. So a big deal is how do we change from one phase to the other? As ice, this is really cold. As liquid, it's like, a medium temperature. And oftentimes as a gas, it's like a higher temperature or a higher amount of energy. So the difference between the three phases of water are that you've got water that has very little energy or is very cold. You've got liquid water, which you've got to add heat to ice to change it to liquid. Or if you want to change from liquid to a gas, you also have to add heat. So going from solid liquid to gas involves energy transformations, either adding heat or getting rid of heat. So the sun adds heat to the earth. And as the sun shines on ice, like we've had a lot of snow melt in the last couple days and or last like week or so, and that comes about as a result of mostly like, the sun shining on earth. And then as the sun shines on the liquid ocean, we get a higher rate of evaporation. And on the other hand, whenever there is no sunlight or you've got cold water currents, gas tends to condense to make a liquid, or liquids then can freeze to make a solid. So there's this issue about energy transformations. So to go from solid to liquid to gas, in this direction, you have to add heat. But if you're going from a gas to a liquid, or from a liquid to a solid, you remove heat. So there's this really big idea about energy transformations that happen on Earth. There are places that are hot, there are places that are cold. The sun adds heat. Loss of energy out into space is how we get rid of heat from the planet. You can add heat with magma in the Earth at volcanoes and whatnot. Oh yeah, I was reading a thing. So as of yesterday at noon, in the 1 week period, there were 17,200 earthquakes recorded in Iceland in the 1 month period preceding. It's been very super active around Iceland, which is really super exciting. There's a difference between the concept of heat and temperature, which hopefully this next chart will help you out. But at the bottom of that page, there's this like triangle here, which is a conceptual way to talk about the names of the phase changes. This is not really that hard in a bunch of different ways. What do you call it when water changes to ice? Nope. It's easy. Freezing. Yep. No, like when liquid water changes to a solid, that's freezing. And do you have to add heat or remove heat to make that happen? Remove heat. Yep. The the technical term for that is fusion, but not to be confused with nuclear fusion. What about going from solid to liquid? Yep, melting. You got to add heat. Now, going from liquid to gas, I told you that there are two different names. There's like evaporation, yep, and boiling or vaporization. Yeah, so evaporation, like evaporation is really easy. Like if it rains outside and the sidewalk gets wet, it'll dry out. You know what I mean? The water evaporates off the surface, but you're not at the boiling point. You don't have to get it to boiling hot temperature. The water will just change from liquid into a gas. It goes into the atmosphere. You know what I'm saying? It doesn't disappear, but it goes into the atmosphere. Evaporation, this is at like, below the boiling point, BP for below for boiling point, but vaporization, that's a specific term we use when we're at the boiling point. Like, and the only time you get vaporization, we'll study like volcanoes that are near water, and you can get vaporization. Anyway, do you have to add heat or remove heat? Yep, you got to add heat. Okay, so then what's it called? We didn't say that yet. When you go from gas to liquid, starts with a C. Condensation. You got to remove heat. And I want to give you examples of how each of these happen in nature. Now, there's another type of phase change that's unusual or peculiar, but it happens with water. You can have water go directly from solid to gas or from gas to solid. Okay, in the wintertime, and actually in the last couple of weeks, we've had like a pretty good snowpack on the ground. And when the sun shines on the snow does not have to melt to decrease its amount of snowpack. Instead, when the sun shines on the snow, that snow can go directly from the solid phase to water vapor. It can even be like really cold and below freezing for a long period of time where the snow never melts, but the snow pack decreases in its thickness because the snow and ice can change directly into the gas. So like if you have a lot of people have automatic like ice makers in a fridge or in a freezer. And a lot of times the ice maker container, so like if this is the reservoir for the ice maker, the ice that's made is always like the same size. But there's a thing to know. If you go down to the bottom of the ice container, you might find that there's ice that's down in there that kind of like, I don't want to say never gets used, but like if it's an automatic ice maker, the auger won't like, shoot that stuff out. Those ice cubes that are down in the bottom there, they're smaller. And they're not smaller because they were made smaller. It's because in the presence of very dry air, and even though the freezer is below freezing, these ice cubes, they will decrease in their size. If you have an older refrigerator where you got to have, like if you have like an ice tray, you know what I mean? Like you got the ice tray and you put the water in, and you put it in the freezer and you wait. If you leave an ice tray, like an ice cube tray in the freezer for like months and months and months, the ice cubes will like shrink. And it isn't because the ice cubes like actually shrink, but the ice from the surface will evaporate. It'll change from the solid to the gas phase. This transition from solid to gas, that name is called sublimation. The most famous thing that does that is dry ice. So like if you ever get food shipped on dry ice, like Omaha Steaks send stuff on dry ice, used for shipping medical stuff. Carbon dioxide at 1 atmosphere pressure can't exist as a liquid. It changes directly from a solid to a gas. So changing directly from a solid to a gas, famously carbon dioxide does that. But in order to change from a solid to a gas, you have to add heat. So ice and snow can change from a solid to a gas. And in this process, going from gas to solid, it's called deposition. That process happened on everybody's car windshields last night. You know, frost, it was never a liquid. You know, like maybe you went to bed and it's below freezing and you get up this morning and there's frost on surfaces. It was never wet. It was never a liquid. Instead, you've got water vapor that's in the air, and when it makes contact with the cold surface of a windshield, it freezes. It was never a liquid. It went straight to gas. So these types of changes, the best example of deposition is the formation of frost. It can also be frost on like snow, except or not snow on grass, but a lot of times that's also like liquid then freezes. The sublimation, this is a good example, is when like the snowpack decreases in its density. So like snow can evaporate. Um, from gas to liquid, this condensation happens with rain, but also with dew. Like, or if you have just like a cold glass and the outside gets wet, that's water vapor hitting the surface and changing to liquid. And liquid to gas, well, this evaporation happens off the surface of the ocean all the time. We already talked about freezing or melting. So um, deposition and sublimation are unusual physical changes, and people stereotypically use carbon dioxide, but these three physical changes, or these six different physical change processes and the three phases, that happens for water on Earth. There are no other substances in your daily life that exist as solid, liquid, and gas. None. When you think of other things, you think like iron, you have a nail, that's a solid. That's it. It's always a solid. You can heat it up to a really high temperature and make it a liquid, but to think of iron as a gas is absurd. Oxygen is a gas. You can really cool it down and change it to a liquid, but the idea of having like solid oxygen is absurd. It's insane. So water is very peculiar in that it exists in all three phases on Earth, and we can change it from any phase into any other phase or state without having to really add or subtract an awful lot of heat. So this is both a topic in chemical oceanography because water is a chemical, but the issues of energy transformation and moving heat around and moving water of different temperature around the Earth, that's also a topic in physical oceanography. All right. I put on the study guide a whole bunch of other useful and important facts. Well, at the top of the third page, I just wrote a thing there where you can write about the difference between evaporation and vaporization. But you can also read about this in the book. Evaporation happens when liquid water changes to water vapor below the boiling point. And most of the water that ends up in the atmosphere as clouds to make snow and ice, snow and rain, happens from evaporation. And then vaporization happens anytime water changes from a gas to a liquid at temperatures above the boiling point. So, a couple weeks ago, there was an unusual weather phenomena where very, very cold air from the Arctic got down into Texas, caused all kinds of trouble, power outages, water pipes breaking, a lot of offshore oil platforms shut down. The ports of Galveston and Brownsville and some of the other ports, they shut down. partly because it was very cold and not used to working in very cold condition. So there's a really cool phenomena that is called sea smoke. And you may have seen pictures like this that's really cool. But this is another kind of peculiar thing called sea smoke. And sea smoke occurs, it's not really smoke. It's not as if something's on fire, but you have very, very, very warm water with incredibly cold air above it. And the reason why they call it sea smoke is that it kind of looks like smoke. It's where the very, very cold water touches, or the very warm air, or very cold air touches very warm water. And it's not a usual condition, but it's really typical whenever you have really super cold temperatures above really warm water. So when I mean warm water, let me go to, this is like Earth at null school, and I can go to ocean temperatures, ocean sea surface temperature. Okay, so what happened uh, a few weeks ago with the very cold temperature in Texas. So Texas is right here. You can actually almost see the outline of Texas because you can see the Rio Grande. The Rio Grande River forms the border of between Texas and Mexico for a large portion of its distance. So this is like where Brownsville is down here. The water in the Gulf of Mexico is usually pretty warm all year round. This red color is fairly warm water. That is kind of orange is getting a little bit cooler. But as compared to water up here in the north, where it's kind of like the greenish and the bluish, that indicates cold water. This water down here is very warm pretty much all year round. In fact, like this red, if it shows it like reddish, that's like swimming temperature. Like not bad to swim in if it's kind of in the reddish color. If it's kind of like yellowish or greenish, that's kind of cool. So when very cold air from the Arctic comes down into the southern states, like around Texas, and then into the Gulf of Mexico, that sea ice is really good. I just saw a really, I can't remember the name of the channel. Let me see if I can find it. There's a YouTube channel of a guy who works on a cargo ship, and let's see. Let me see if I can find it real quick. Cargo Galveston. Let me do sea smoke. I don't know. Let's see. Life on, I think that might be the guy's channel. This might be the guy. Actually should have saved it. Is that him? Yeah, this is him. Okay. I don't know if this was the right one. It was almost eerie looking how much. Oh, here it is. Yeah, this is really good. Probably one of the best examples I've ever seen of what sea smoke looks like. I know it's like choppy, but I'll put a link to this video. Um, so what happens is the water is relatively warm, and that warm water evaporates at a pretty fast rate anyway. And see the like the white lines on the water, that's actually water that evaporates very quickly, but then as soon as it hits the cold air above it, because the air is below freezing, it instantly condenses. So you're actually making a cloud just inches above the surface of the ocean itself. And that only really happens if you have incredibly cold air meeting very, very, very warm water there. It becomes a hazard to navigation too, because if the sea smoke is like thick enough, and again, it's not really smoke, it looks like fog. Fog is an example too of air, you know, high humidity air where it begins to condense and you're actually like within a cloud. But this channel is pretty good if you want to learn about shipping or care about shipping or something like that. Then as the day goes on, the air warms up, and as this is now later in the day, and as the air warms up, then the sea smoke dissipates, and it's not so like smoky looking. Anyway, this guy just talking about like his life on a cargo ship, and what you do on a cargo ship. A lot of stuff in this world is shipped by a cargo ship, and we're going to look specifically at the economics of cargo ships and how that helps us out with oceanography. But I don't know if you know much about cargo ships, but uh, these are what are called IBCs, integrated bulk containers. And let me get into open image. So like these are large cargo ships. Those are IBCs, integrated cargo or integrated bulk containers. They're standardized for transportation all over the world. Those are each the size. Those are each they put them on top of a trailer, and those are each one tractor trailer in size. So not only do they have, I don't know how many rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 23 rows wide, and then there are 8 tall here, but there's also, they're all down into the cargo hold. And this ship drafts about twice the height of what's above the water. So the side of the ship is here, but there's also as much ship underneath the water. So there's about 16 high, 23 wide, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like about 23. So there's about 8,500 containers on the one ship. So you load that bad boy up, 8,500 tractor trailers worth, go across an ocean, get yourself to a new continent, unload them. And that's a lot of like clothes, appliances, everything that's shipped between continents goes in these integrated bulk containers. These containers are designed to then be stacked too high, too tall on a train, or individually loaded onto a tractor trailer. So these containers are designed to be stacked on board ships, stacked too high on a train, or go on a bed of a tractor trailer. So you can move them anywhere in the world in all three like all three methods. And you can't move cargo per mile any cheaper than you can by ship. Ship is the cheapest. Then it goes train, and then tractor trailer is by far the most expensive way to move the containers. So you try to move them by ship as much as you can, then move them by rail, and then finally, when you have to, move it by truck. All right, so then underneath that evaporation and vaporization stuff, I wrote some facts there about unusual thermodynamic properties of water. this is just a brief description of also what's in the textbook. Water has a really high melting and boiling point, has a very high heat capacity. So we're going to look and see at the difference between heat and temperature, but it takes an awful lot of heat to change the temperature of water, which helps with the planet as a whole. Because since the planet is covered in 70% of the planet is covered in water, and it takes a lot of energy to change the temperature of water, the water on the planet acts to regulate the temperature of the planet to a huge extent. And people who live in coastal areas don't experience as much of a change in temperature from day to night as people who live inland. Like if you live in the middle of a continent at high elevation where the air is very dry, you can have huge changes in temperature from day to night. But if you live like, you know, near the shore or on a beach, the difference in temperature from day to night is much, much, much smaller. And it's the presence of all that water that plays a big role in preventing the changes in temperature so much. All right, so tomorrow I got this. There's a lab on the water cycle to look to see where water goes on the planet and spends different portions of time on the planet. And we have a water testing lab that we'll do to test different properties and presence of chemicals in both freshwater and saltwater. And we'll deal with how water acts as a thermal regulator on the planet. All the diagrams in the study guide are in color when you if you view them like on Schoology.